Welcome to this lecture on recursion and another kind of induction called structural induction. In this segment, we're going to focus on recursion. As you're probably aware already, recursion is widely used both in discrete mathematics and in computer science. Many objects are recursive. In fact, in this course and in your other computer science courses, you will discuss recursive functions, recursive sequences, recursive sets, recursive data structures, recursive algorithms, and so on and so forth. So what is the general definition of recursion? Well, the most general characterization of recursion is that the object being defined, if it is recursive, refers to itself within its own definition. So the most familiar recursive object to you is probably a recursive function right now. So let's take a recursive function and apply this definition of recursion and see how it applies. So a function is defined by a body. So if the function is recursive, so it's being defined by a particular set of instructions that make up the body of the function. If that function is recursive, that means the body of the function must be referring to the function itself. And what we mean in programming is that the function is calling itself within its own body. So the danger, of course, of recursion is the circularity or infinite loops. So in a recursive function, for example, to avoid circularity, we want to make sure that whenever the function calls itself, it does so with values of its arguments that are smaller than the values that you started out with. So if the values get smaller and smaller, then at least you can go into an infinite loop. But for that to happen, you must also have one or more base cases, that is, values of the arguments to the function, for which the function can compute its value directly without making recursive calls. So in conclusion, a recursive function must be defined with at least one recursive case where the function calls itself with smaller arguments. It's like a smaller version of itself. And at least one base case where the computation is direct without any need for a recursive call. This is like a building block of the function definition. And more generally, any recursive entity, whether it's a function, an algorithm, or a data structure, is defined in terms of both smaller versions of itself and non-recursive building blocks. Now, it's very common to prove properties of these recursive entities by induction. In fact, recursion and inductions are very strongly connected. You might say they are two sides of the same coin. For example, think about the similarities between the basis step in proofs by induction and the base case in recursion. In a basis step, you can complete the proof without an inductive hypothesis. And in the base case of recursion, you can complete the computation without a recursive call. Furthermore, consider the similarities between the inductive step in proofs by induction and the recursive case in recursion. In the inductive step, you're proving p of k plus 1 using p of k, whereas in a recursive case for recursion, say let's take the factorial function, you're computing f of k based on f of k minus 1. So clearly, recursion and induction are very strongly related. Now let me conclude this segment by looking at three concrete examples of recursive functions. I'm going to give you their recursive definitions, and I'm going to ask you to infer what the function is. So the first function, f of n, is defined as follows. It's equal to 1 if n equals 0, that's the base case, and it's equal to f of n minus 1 times n if n is positive. So what function is that? You got it, that's the factorial function. So make sure you review it and you are very familiar with it. Now the factorial of n, or n factorial, is the product n times n minus 1 times n minus 2 times 2 times 1. How about this recursive definition? Well, it should be very familiar to you. This is the Fibonacci function. So I'll just write it down here. Just make sure you're very familiar with that one as well. Notice this one is doubly recursive because the definition of f of n, at least in a recursive case, contains two recursive calls, or calls to itself. And notice in both cases, of course, the value of the argument, n minus 1 and n minus 2, is smaller than the original value n. And in this case, because we have two recursive calls, we have two base cases. Now finally, let me give you a third recursive definition. This time it's a function of two arguments, m and n. And the recursion happens only on n. So if n is equal to 0, then the function returns 1. If n is positive, then the function returns f of m, comma, n minus 1 times m. So I will let you think about this function, and you should be able to figure out what it computes.